on the right. Another sort of advantage combine them into an array of pairs, and then we can unpack those pair of values, which are values from nums1 and nums2. We get pretty much what we expect. Reversing an array is as simple as calling the reverse method on that array. So 1, 2, 3 becomes 3, 2, 1. Sorting an array is just as easy. Taking this array, we can call sort on it. So this will sort it in ascending order by default. If we want to sort it in reverse order, we just pass in the parameter reverse equals true, and then the array will be sorted in descending order. We can also sort a list of strings. By default, they will be sorted based on alphabetical order, as you can see on the right. But if we want to implement a custom sort, for example, if we want to sort based on the length of each string, then we can do that by passing in a lambda function. So in this case, the key is equal to lambda, which is basically a function without a name. And we're going to take every single value from the array, call it x, and then return from that the length of x. And this is the key that's going to be used to sort the string. So each string is going to be mapped to its length, and then we're going to sort those strings based on their length. So by default, it's going to be in ascending order, as we can confirm on the right. Another sort of advanced way to initialize lists is using list comprehension. So if we wanted to go through every value in range 5 and call that value I, and we want to add that value to this array, this is the shorthand. So we're iterating for I in range 5, and then I is going here. So we're taking that I value and adding it to the array, and printing it, you can see that we indeed have 0 through 4. Now maybe we want to go through every value in that range, but we want to take I and add I plus I to the result. So for every index, we want 2 times that index added to the result. You can see we can also do that pretty easily. If you want to do something similar for a 2D list, it's also pretty easy, but maybe a bit different than you would expect. The easiest way to do it is the shorthand that we talked about earlier, where we take an array with 0 and then multiply it by 4. This will give us an array of size 4 with all zeros. And we want this array to be added to the outer array 4 times. So we have an inner loop for I in range 4. We're not even using the variable I here, but this will build a 4x4 grid of all zeros. You might be thinking, isn't there an easier way to do that? Well, actually not. You might be thinking, can we just do this, create an array of size 4 and then multiply that by 4? Well, technically this will work, but each of the 4 rows of this array are going to be the same. So if we modify one of the rows, we're going to be modifying all of the other rows. We're not actually creating 4 unique rows in this case. It's a common thing that can throw people off. If you have more questions about this, feel free to ask in the comments. It's something that tripped me up a lot when I first started. Strings are pretty similar to arrays, so we can declare one with double quotes. You can also use single quotes if you want, and we can slice them the same way we do with arrays, and printing it works the same. But a key point is that they are immutable. That means we can't modify the string. That means we can't reassign the character at index 0. We can, however, update the string, but updating it will actually create a new string. So adding def to the end of the string will create a new string. So basically, anytime you modify a string, it's considered an end time operation. Strings can be converted into integers, and then those integers can be added. Integers can also be converted into strings, and then those strings can be added together. So when you add 2 integers together, we get an integer as the result. Adding 2 strings together appends those strings together. So we get 1, 2, 3, 1, 2, 3. If for some reason you need the ASCII value of a character, you can do that with the OR function. So printing this, you can see we get 97 is the ASCII value of lowercase a, 98 is the ASCII value of lowercase b. You can also join a list of strings together with a delimiter. In this example, we have 3 strings and we're joining them with the empty string delimiter here. So we're basically just appending these 3 strings together. We could also have had a delimiter, maybe a space in between all of them, and printing the result, we get all 3 strings appended. Queues in Python are double-ended queues by default. You can import them. Adding values to the right side is as easy as appending to the queue. So at this point, our queue isn't much different from a stack, but the benefit is that we can actually pop from the left of the queue, and we can do this operation in constant time, unlike with a stack. as you can confirm on the right. Since it's double-ended, we can also add values to the left of the queue. So the one that we popped, we can add back to the left side. And also we can choose to pop from the right side if we want to. So running this, we can confirm that the 1 is added back, and then we pop the 2 after that. Hash sets are really useful because we can search them in constant time and we can insert values also in constant time. Of course, there won't be any duplicates in our set. Of course, unlike a list, there can't be any duplicates in a hash set. But we can just as easily get the length of the hash set to know how many elements have been inserted. We can also search the hash set without a function. We can use the in operator. So if we want to know if 1 exists in the hash set, same thing with 2, same thing with 3, which we know does not exist in the hash set, as we can confirm. We can remove values also in constant time and confirm that the value has indeed been removed. To initialize a hash set with a bunch of values, we can actually pass in a list. But just like with lists, we can also do set comprehension and manually initialize it with a loop inside of the hash set. So here we're going through every value in the range of I and taking that value I, adding it to the hash set, and initializing it this way is identical. Hash maps are probably the single most common data structure you're going to be used, and this is what we were saving those curly braces for. To insert, we simply take some key value, in this case a string, and assign it to another value, in this case a number 88. And we can add a bunch more. Just like with hash sets, we can't have duplicate keys inside of the hash map. Printing it is just as simple. Taking the length will give us the number of keys that exist in our hash map. We can modify the value that's mapped to a key, so we can change Alice from being 88 to 80. We can also search if a key exists in a hash map in constant time, and we can also remove that key, which will also remove the value, as we can confirm on the right. To initialize a hash map, we can add pairs inside of the curly braces, where each pair is separated by a comma, and the key goes on the left side of the colon and the value goes on the right side. This is the same as manually inserting values into the hash map. But if you want to get even more fancy, you can use dict comprehension. Hash maps are basically called dictionaries in Python, and the syntax is pretty similar, but in this case, if we're looping I in the range of 3, we're going to have two values. I, in this case, is the key, then a colon, and then the value goes after that. In this case, we're mapping I to 2 times I. This is pretty powerful, and I find that I use it most frequently when I'm doing graph problems and trying to build like an adjacency list. Looping through a map is pretty interesting because there's many ways to do it. By default, we iterate through every single key, and then we can, print that key and also print the value that that key maps to. But also, we can directly iterate through the list of values of that hash map if we don't even need the key. Lastly, using unpacking, we can actually go through the items of that map, which will give us the key and the value. This is pretty similar to the first loop that we have. I guess it's a bit more concise to write it this way. Python also has tuples, which are pretty similar to arrays, except to initialize them, we use parentheses rather than brackets, and they are immutable. So while we can index them, we can't modify them, so this won't work. You'll mainly be using tuples as keys for a hash map or a hash set. So in this case, we're mapping a pair of values 1, 2 to 3. So this tuple is basically our hashable key. We can do the same thing for hash sets, of course. And then we can use that tuple to search the hash set. The reason we do this is because lists are not hashable and can't be keys for hash sets or hash maps. So this here will not work. Heaps are another really common data structure to find the min and max of a set of values frequently. Under the hood in Python, they're implemented with arrays, of course. So actually to create an empty heap, we just create an empty list. And to push values to that heap, we use heapq.heapPush to that min heap the value 3. By default, heaps in Python are min heaps. So we push a few more values, and then to get the minimum value, it'll always be at index 0. That's just how heaps are implemented. To loop through a heap, while the length of the heap is non-zero, we can also pop values from the heap with heapq.heapPop from that min heap, and then print the corresponding value that we just popped. Since it's a min heap, we'll see the values are printed from smallest to largest. While Python doesn't have max heaps by default, the workaround is basically to multiply each value that we push by -1, and then after we pop that value, we also multiply it by -1 to negate the original -1. So if we wanted to implement a max heap and push the value 3, we would actually push -3, and if we wanted to push 2, we'd push -2, same thing with 4. Again, the max will always be at index 0, but we know we have to multiply it by -1 to negate the original -1. By popping each value and multiplying multiplying it by -1, we can confirm that the values are printed from greatest to smallest. Now, if you already have the initial set of values that you want to build the heap from, you can do it in linear time by calling build heap, or in Python, it's called heapify. So we can call heap_q.heapify this array. And while that array is non-empty, we're going to keep printing the values, and we can confirm that they're printed from smallest to largest. Functions in Python are pretty straightforward and concise. We use the def keyword, we name the function, and then we pass in some parameters, in this case n and m. Just like with conditionals and loops, we use a colon after the declaration of the function, and the body of the function is going to be indented. So we're returning the multiplication of those two values and printing the result. One functionality I use a lot in coding interviews is nested functions. This can be really helpful in recursive problems because if you have an outer function that takes in a couple of parameters and you also declare some values in that outer function, the inner function will actually have access to all of those variables by default. So then if we called the inner function, we don't even have to pass in a, b, and c. Now this is a pretty simple example, but if you've watched any of my graph videos, you know how nice this can be in keeping our code concise. One thing that trips a lot of people up with nested functions is that you can modify objects, but you can't reassign values unless you use the non-local keyword. So if we have a function that's going to double every value inside of an array and also double this value itself, this is not an array, we can have a helper function. It'll have access to both of those outer variables. We can modify the array pretty easily by going through each value in the array and then doubling it. This works and will update the original array. But if we double the value, it'll only double the value in the scope of the helper function. If you want to update the value outside of the helper scope, you'll have to declare it as a non-local value, and doing this and then modifying the value will modify the original values. And then in the outer function, we can call the helper function without passing in the variables and then print the variables. Now to actually call the double function, we can create some variables, call it, run the code, and we can see that each variable was doubled. Again, this is a trivial example, but if you're familiar with my videos, you know that this can be helpful. Classes are also pretty concise, but a bit more limited than other languages. A constructor is basically _init, _ after that. That's kind of the name of the constructor in Python. Self is passed into every method of a class. It's basically like the this keyword in other languages. In this case, our constructor is maybe taking a list of numbers. To create member variables, we also use the self keyword. So this is creating a member variable called nums and assigning it to the nums that were passed in as a parameter to the constructor. We can also create a member variable for the size of nums by taking the length of the parameter. To create a method for this class, for example, getLength, we don't want to pass in any parameters to this, but we have to pass in the self keyword always. That'll give us access to our member variable, which we're going to return self.size. If we want to call another member variable from a member variable, in this case, we want to call getLength from this other function, getDoubleLength, we can do that again with the self keyword. This is a pretty useless example, but I'm mainly trying to explain the syntax and the structure of classes in Python. Now, this is more or less everything I've needed to know for coding interviews. It's surprisingly not a lot. And you don't have to memorize any of this. As you solve coding problems and as you prepare for interviews, you might have to look up the syntax, or how exactly do I use heaps? How exactly do you use double-ended queues? Things like that. It's perfectly okay. But after you practice enough, most of this stuff is pretty easy to get down. It doesn't even feel like you're writing code after a while. Python is a pretty big reason I was able to get a job at Google, in my opinion. Now, if you're preparing for coding interviews, check out neetcode.io. There's a ton of free resources to help you prepare. Each practice problem listed has a thorough video explanation, and we have code support for Python, C++, Java, and JavaScript. If you're new to data structures and algorithms, I've got some really helpful courses, not only for beginners, but also for advanced users. Thank you so much for watching, and hopefully I'll see you pretty soon. On the right. Another sort of advanced way to initialize lists is using lists. But how do you actually get good at LeetCode? Let me explain. When I first started doing LeetCode problems, I realized this is the most academically difficult thing I've ever done in my life. I had taken AP Calculus and physics and a bunch of really difficult things in high school. And in college, honestly, college for me was a little bit easier than high school. I remember everyone would always say, high school is hard, but wait until you get to college. College is going to be really hard. That's when you're going to have to learn how to study and improve your study habits and everything. For me, I think when I took my first programming class in college, that's when I struggled a little bit. But after that, at least for me, I went to a pretty average college. It was relatively easy, I'm not going to lie. But you know what was difficult? When I started hitting leak code problems. I wish somebody had told me, leak code is not easy. This is the hardest thing you're probably going to do to get a job. It's going to be harder than all of your classes that you've ever taken. When I took my first programming class, like I said, I struggled a little bit at the beginning. So for me, programming was actually harder than these other technical subjects. But now I tell myself I was just in that machine learning phase where I was just taking in a bunch of new data, understanding how to use it. And then eventually I got familiar with it and then I was good. I wish I could say the same thing about leak code. Every time you think you're good at it, you see a crazy problem and it just destroys your confidence. It's completely different than anything you've ever seen before. So what is so different about leak code than everything else? Is it really harder than everything? Like when I was doing it, I just thought, damn, I guess I'm just not smart enough. I thought I was a genius my whole life doing everything so easily, getting A's whenever I wanted to, but damn, this thing, I just can't do it. I don't think it's about intelligence at all. Believe it or not, it's about systems. It's about processes. It's about methodology, how you're doing it. At least that's my opinion, and I'm going to try to convince you why. First, let me show you how I learned leak code when I first started. You have a problem, a hard problem, median of two sorted arrays. It's the fourth leak code problem. Imagine how many people came across this problem and just wanted to jump out the window after. Of course, most people can't solve it, so what do? Well, back in the day, leak code didn't really have articles and editorials, and even this one is paywalled. So you end up going to the Solutions tab. It used to be called the Discuss tab. Nowadays, if you go here, you'll click one of these, and man, you'll see this beautiful explanation. Look at this. This guy's explaining it with hints, with everything. It doesn't have any pictures in here, but sometimes they even have pictures. It's reasonable to be able to understand one of these solutions. You can see this one was recent, right? 2023. Back in my day, though, we didn't have that. This is what we used. We used these solutions, and also Lee 215, if you've heard of him. But look at this. Look at this solution. First of all, just look at it. Crazy solution, and not much of an explanation given. Okay, the second one is, I guess, a little more reasonable. I don't know. Even though the third one is definitely a little bit more reasonable, there's not really much of an explanation. You go down here, you don't see much of an explanation, at least back in the old day, like 2019 when I was doing it. Everybody's just asking, can you actually explain it? And nobody did. Okay, the best you'd get is like 5 comments here. So I know I make videos on these problems and sometimes I don't do a perfect job either, but you have to realize that it's tough love, okay? I can't explain every little detail in a 20-minute video. I can do the best to give you the intuition of why a solution works. Even that, in my opinion, is a lot easier than how I learned. This is how I learned. I would look at these solutions, for hours and hours, try to figure out why they worked. And finally, when I did, I would try to make a video explanation for it. Thankfully, now we do have a lot better resources. But even then, leak code is still not easy. Why isn't it easy? So if I'm arguing that leak code actually isn't much more difficult than math or physics or some other highly technical subject that you have learned before, why does it feel so much different? And I think one big reason is the process, the methodology, the way that you learned these things versus the way that you're trying to learn this. Let me just kind of rewind, take you back through time and remind you, how did you learn math when you were a kid? You probably first learned how to count, like 1, 2, 3, 4, and just learned the base 10-digit system. And then you probably learned bigger digit numbers, 100, 110, 234, something like that. And you were able to then start adding numbers together, 1 plus 2, and then bigger digit numbers, 3, 4, 5, 1, 2, 3. Do you think if I successfully explain to a child how to solve this problem, and they are able to do it, they are able to take these digits and add them together and get that big number, and then I make it more complicated and I teach them how to carry a number to do more complex addition, maybe subtraction. If I show them how to do that, just a single time, or maybe even several times in the same day. And then maybe a week later, a month later, I show them the same thing and they don't practice in between that week or month. I give them a similar problem. Do you really think they'd be able to solve it? Probably not, unless they're really, really smart. The point I'm making is you could teach somebody how to do something difficult. They do it a single time. They think they understand how to do it, but if a bunch of time goes by, you're probably not going to be able to do it again. Kids learn the same way adults do, with repetition, right? So that's a pretty simple answer, repetition. So why don't more people do it? I mean, it just sounds so simple. Why don't more people do repetition when it comes to LeetCode? Let me kind of explain the classic problem people make when they solve LeetCode problems. Let's say they're solving a medium binary search problem. And I bet you most people who try to solve a medium level binary search problem, they're probably not even super good at basic binary search. But okay, they try to do it. It takes them probably some cognitive energy to even implement basic binary search. If it takes you 10 minutes to implement basic binary search, that's a problem. You shouldn't even be attempting medium problems. If it takes you, 10 minutes to figure out that this number is 234, why are you doing addition? You don't even know what this number represents, right? You got to get really, really good at the basics before you kind of take steps beyond that. But okay, just continuing. You get to a medium binary search question. You realize that it's a binary search question, but you still can't solve it. All you have is your basic binary search algorithm implemented. Then you look at the solution. It takes you maybe 1 hour to understand the solution, but you're able to do it. You write your code, you kind of really exercise your brain muscles, you write it, and now you're done for the day. Then you continue solving LeetCode problems. Maybe a month later, you solve another medium binary search question. You're not able to solve it. You look at the solution. It takes you some time to figure out the solution. Once you realize it's binary search, you feel bad. You realize it's similar to a problem you've already solved, but you weren't able to figure it out again. Why not? Because you tricked yourself. You think you understand the solution, and maybe you did for a very short time, but that didn't really sink in. And it's not your fault when you're learning something that's genuinely difficult. Like if you're reading the solution to a problem, it's difficult and you think you understood it, which you might have, but it didn't sink in. So of course you need repetition. It's such a simple answer, isn't it? Just practice. But then why isn't anybody doing it? This is how you learn pretty much everything in life. When you learn how to read, it takes practice. Why don't people do it when it comes to LeetCode? I don't know, but let's be honest, I made the same mistake until I realized this. I thought I did so well in high school. I did so well in math and physics. So why am I so bad at LeetCode? Because the way I'm practicing it isn't enough. LeetCode is difficult. It's difficult like math and physics, but it's not more difficult. You could not teach somebody how to count and add numbers and divide numbers in a relatively short time without practicing. So now let me try to give more concrete advice on how to practice, how to actually do repetition, because even that isn't as straightforward as you might expect. First of all, there are certain core algorithms like binary search, DFS, depth first search, breadth first search, sliding window, and a bunch of other kind of core algorithms that I talk a lot about on this channel, as well as you can check a lot of this stuff out on neetcode.io. But my personal advice to you would be get really, really good at these basics. Practice them a lot. You can do that at the same time that you're solving LeetCode problems, or you can do it before you start solving LeetCode problems. But you want to get good at it. And I promise you, it won't take you that long. The target that most people set when they're solving LeetCode problems is, I want to be able to look at a LeetCode problem and solve it quickly. That, in my opinion, is the wrong target. You should get really good at just core algorithms. That should be your target. At least that should be your first target. And binary search, it's a very short algorithm. What is it? like less than 10 lines of code, I think. Every computer science student learns it. Maybe the first time you do it, it'll take you like 30 minutes or an hour to like fully understand it. Okay, the next time you implement it should probably take you like half that, 15 minutes. The third time you do it, I bet it'll take you like 10 minutes. And the fourth time, probably like 8 minutes. Eventually, you should get to a point where you can implement this in less than 5 minutes. I could probably do it in like 30 seconds, to be honest, because it's not that much code. You could say I memorized it, or you could say I deeply understand it. You could say whatever you want, but the point is I could implement it very quickly. So now when I get to a medium difficulty LeetCode problem, the binary search aspect of that problem is trivial to me. It's like 1, 2, 3, like numbered systems. It takes me no cognitive energy to focus on implementing binary search or understanding why it works, understanding why it's efficient. Any of that doesn't take me any time. To get to this level, suppose it just takes you like implementing binary search 5 times. And I probably implemented it, dozens of times, but there is like diminishing returns. If you can implement binary search 10 times in the period of like a week or a month, you can probably get just as good at it as I am. Some of these other algorithms are probably a little more difficult, DFS, BFS, but the same idea can be applied to those. Implement these 5 times, 10 times, whatever. It'll probably take you a few hours to do that. Let's say 4 hours to implement it like 10 times. Now, you don't understand. You have such a big advantage when you look at LeetCode problems now. Like, you really don't understand it until you've experienced it. When you've been in my shoes, many of you who are good at LeetCode probably know the feeling. These things are so trivial to you that medium problems can also be a lot easier. Now you actually have the brain capacity to focus on how you can take these algorithms and actually apply them to a medium problem, which takes a lot of energy. You're not kind of juggling 2 things at once. You're not trying to remember, how do I implement BFS? And also, how do I apply it to this difficult problem? You're not doing that. I don't know why when somebody solves a LeetCode problem and then they look at the solution, they feel bad about that, but they look at the solution, they're able to solve it. Why not solve the same problem the next day? Why not? Do you think you're going to lose anything by doing that? I guess it takes time, but if that problem is fresh in your mind, it might not take you more than like 15 minutes. So why not do it? You're reinforcing something that is good. I promise you, anybody who's really, really good at LeetCode or a really good competitive programmer, this stuff is literally like ABCs to them. You have to do that to get good. You can call it cheating, you can call it memorizing, but that's just how it is. And I know for a lot of people, this isn't fun, but in my opinion, it's pretty fun being able to go into an interview and be able to solve it and then get, a high paying job as a result. Even if you agree with everything I've said so far, there is some more nuance to this. LeetCode is more difficult than just what I've talked about here. Some problems are definitely more difficult than just taking something and applying like a core algorithm to that problem. I'm specifically talking about hard problems and even some medium problems. I think the next level of getting good at this stuff is similar to what I'm talking about, repetition, practicing in a smart way. But I think the next level is asking the question, why does something work? Most people think math is just memorizing numbers, formulas. You have some formula, F equals ma in physics. Once you know what the force is, the mass is, the acceleration is, you just take those values, you plug them in, and then you get some value as a result. That's what people think math is. What math really is being able to argue why the math works in the first place, aka proofs, right? You might have taken a discrete math class in college or some other class where you had to do math proofs. And this is kind of the second component to LeetCode problems. In my opinion, the more complicated component. You might have looked at a LeetCode solution or watched one of my videos. Even though the algorithm made sense, it might have been an algorithm you're familiar with, you still didn't fully understand why it worked. And the why is so important because if you want to be able to solve a problem for the first time, you have to really understand why. The repetition I talked about before will only take you so far. What I'm getting at is it's not just about being able to quickly write out the DFS algorithm or BFS algorithm from scratch. It's about understanding exactly why it works. I try my best in my videos to explain this, but it's not always easy unless I want to make like an hour-long video. My advice to you for figuring this stuff out is just spending some time thinking about it. I know that's kind of an obvious answer, but it's the only answer. Nobody can force you to do it. No matter how well of a resource you find, whether it's an article or a video, nobody can go in your brain and actually force you to think about why something works. And you do need a little bit of curiosity for that. For example, there is an algorithm called two pointers. It's applied in many cases to like binary search, you need 2 pointers, and in sliding window, you need 2 pointers. And there's a condition in problems where you'll have something like while the left pointer is less than the right pointer. This is the condition. Sometimes though, you'll have the condition while left is less than or equal to right. And I've had some people ask me the question, how do you know whether it's this or whether it's less than or equal? And they try to memorize it. But I don't think it's worth memorizing. I think you have to really look at the context of the problem and figure out why that's the case. The easiest thing would be to come up with some examples. I think people watch my videos sometimes because I'll have like an example and walk through it. Why can't you do that by yourself? Why can't you bring out a pen and paper and just walk through an example by yourself? Is it because you're lazy? Because I promise you, I wouldn't have gotten good if I didn't do this drawing. And I only do the drawing for my videos. When I'm practicing something by myself, I'm using pen and paper. So if you're the type of person, when you get stuck, you just kind of go blank, you just stare at your screen, you're just thinking in your head, try to do something else. Try to type out some notes, some comments as you're trying to code up a solution, or, use pen and paper. If you're not doing that, you're missing out. I promise you, anybody who's really, really smart only got good at it by practicing, by thinking of creative examples, by thinking of edge cases that would maybe break a solution or maybe would reinforce a solution and explain why exactly that solution works. I think if there's anything that you have learned from this video, it's that a lot of the things you did as a kid and maybe you stopped doing as an adult were very, very useful to you, like taking handwritten notes, explaining your thought process, repetition, even boring repetition, even doing something so many times to the point where it just gets so boring. That's kind of what math class was as a kid. Those things are useful. Like the structure that is forced on you when you're a kid is very, very useful. And I think having too much freedom as an adult is not. When you have like 8 hours in a day, it's easy to procrastinate. But when you're a kid, you have like 1 hour with this class, a second hour in Spanish class or whatever. And that kind of, structure is pretty useful when it comes to learning. There's a reason why everybody does it all around the world.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem binary search. We're given an array of integers nums, which are going to be sorted in ascending order, and we're also given a target integer that we're going to look for. If the target exists in the array, then we can return the index of it. If it does not exist, then we return 1. The goal is to create an efficient algorithm that can run in log n time. So what algorithm are we going to use? Well, the problem pretty much tells you binary search. So while this is self-explanatory and a pretty basic algorithm, I still think it's really important because a lot of problems kind of extend the idea of binary search and then make it even harder. And this is actually a pretty common interview question, to be asked some variation of binary search. So this is a very good problem to practice, and your goal should be able to implement binary search very quickly, basically as if you were doing it in your sleep. So I'll try to explain this quickly, but also in a beginner-friendly way. So the input array is sorted. The target value could exist anywhere in this array, or it might not exist at all. When we start, we are considering the entire input array. How are we going to do that? Well, we're going to have 2 pointers. One pointer is going to be at the leftmost index, which is initially index 0. Another pointer is going to be at the rightmost index. These pointers mean that we are considering the entire range. Now, if we could only look at one of these values, which one should we look at? Should we look at the leftmost? If we do that and we see that it's not equal to the target, then we've only eliminated one possibility and we still have to search all of these. If we look at the rightmost, similarly, it's not the target, so we've only eliminated one possibility. We still have to look at the rest of them. But if we look at the midway point, and technically either of these could be the midway point, the way we calculate it though is going to be literally taking the left and right indexes and dividing them by 2, which I think will lead us to this position. But approximately the halfway point. Why should we look here? Well, we can compare it to the target. It's not equal to the target. So what does that tell us? Have we only eliminated one possibility? No, because remember, the input array is sorted. So if this is not equal to the target, we should also ask, is it smaller than the target or is it larger than the target? In this case, it's smaller than the target. So if this is smaller than the target, then everything to the left of it is also going to be smaller than the target. So this was our midway point, we'll call it M, and we found that it's smaller than the target, so we can eliminate these 3 values from consideration, everything over here. How are we gonna, represent that in code? Well, we're gonna take this left pointer and then shift it to be M plus 1. So now our left pointer is going to be over here. This represents possible range of solutions is going to lie within, these 2 pointers. So at this point, we're just going to repeat the algorithm, repeat what I pretty much just did. Now, if we take these 2, add them together, divide by 2, the middle is going to be over here. So then we're going to check, is this equal to the target that we're looking for? In this case, yes, it is. So now we can return the index because that's what we were trying to do. We can return M, whatever it happened to be. I think it's 4 in this case. So that is pretty much the idea of binary search. Okay, so now the time complexity. If you know binary search, you already know that it runs in log n time, but let's quickly understand why. So we're not considering this example anymore, but suppose we had 16 values in the input array. Every time we go to the midway point, we either find the target, but if we don't find the target, we know we're at least going to eliminate half of the possibilities. So we would eliminate this down to 8. Now we're only looking at 8 values. We still don't find the result. We keep dividing it by 2. We make it 2 remaining and then finally there would only be one value remaining. And either that's going to be the target or it's not going to be the target, and then we're pretty much done with the algorithm anyway. So the question is, if we have a while loop, the while loop is going to run as many times as we can divide the length of the input array by 2. How many times can we divide it by 2? Well, if you remember from, this is too much math, higher input array as our search area. So our left pointer is going to be at 0, our right pointer is going to be at the last index, which is just the length of the array minus 1. Now we want to continue going until there's no more possibilities left, or we have maybe found the result. So the way to do that is to basically say that while our left pointer is less than or equal to our right pointer. Because I didn't show it in the drawing picture, but suppose we just had a very small input array just to illustrate our mid, we'd say, okay, this is too small for our target. So we're going to set our left pointer to be equal to mid plus 1. So that means our left pointer would be 1 and our right pointer would be 0. That basically means our left pointer has crossed our right pointer, and that's how you know that we have no more values left to search. We did not find the result. So that's why we're doing less than or equal. If they're both equal though, if they're both pointing at this value, that means going to find the midway point, which we can get by taking L plus R and dividing by 2. If the value that this index is at is greater than the target, then we want to look at all values to the left of it. So we're going to take our right pointer and set it to M minus 1. We want to look at all values to the left. We're basically shrinking our criteria. And in the other case, else if that num is smaller than our target, then we're going to do the opposite. We're going to set left equal to mid plus 1, just like in the drawing explanation. The last case is if neither of those are true, that must mean that we found the target. If it's not greater and not smaller, that means it must be equal. That means we can return M, which is the result. But if we went through every iteration of the loop and we didn't find the result, then outside of it, we are told that we should return -1 to indicate we did not find a result. So that's the solution. Let's run it to make sure that it works. And as you can see on the left, yes, it does, and it's very efficient. It doesn't exist in Python because Python integers are unbounded. They can pretty much be infinitely large. But in most languages like Java and C++, you might encounter an overflow, because suppose we had a very large input array and then these two integers were very close to the 32-bit integer max, which is something like 2 to the power of 31. Suppose they were both close to